Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 4.6 from your textbook, which introduces you guys to the concept of a basis. And as we'll see right away, the defining a basis is going to be the very first thing that we do. Basis basically combines the two major concepts that we've been studying in the previous sections, namely the idea of a spanning set and the idea of linear independence. So we're going to jump right in, define a basis, talk a little bit about some theorems that apply to the properties of a basis and a concept called the dimension of a vector space, and we'll also get a chance to look at sort of the standard basis or dimension of a couple of our sort of main vector spaces. So let's go ahead and start off with our definition here. So a set of vectors v1, v2 through vn is called a basis for a vector space V if those set of vectors have two major properties. First, v1 through vn must be linearly independent. So, in other words, none of the vectors can be linear combinations of the other vectors. So, the only solution to c1 v1 plus c2 v2 plus cn vn equals the 0 vector must be where c1 through cn are all uniformly 0. So, those vectors must be linearly independent, and the vectors must span V. So you can see how this concept of being a basis combines what we've been doing in the previous two sections. In other words, a set of vectors is a basis if they're linearly independent and they span the overall vector space. A follow-up definition to this is if a vector space has a basis, it is said to be finite dimensional, and we'll see in a moment that dimension is a well-defined concept. It'll turn out to be that the amount of vectors in a basis is equal to the dimension. We don't quite know right now that that's a well-defined concept. In other words, we haven't proven that every basis is the same size, but we will do that in just a moment. But I do want you guys just to have this definition. If a vector space has a basis, we call it finite dimensional. There are, however, vector spaces for which no basis exists, and we call those infinite dimensional. And we won't really talk about any of these vector spaces until like the next video. So pretty much everything we're going to be discussing in this video is going to be about vector spaces that are finite dimensional, meaning that they do have a basis. Okay. So the very first thing we're going to do is basically prove that this concept of the dimension, which is the amount of vectors in the basis, is a well-defined concept. Basically, we're going to try to show that every basis for a vector space is the same size. So we're going to do that in our next theorem here. All right, theorem. Every basis for a finite dimensional vector space V is the same size. So we have this phrasing of finite dimensional vector space V to guarantee that the vector space has at least one basis, and then we're going to show that every basis must be the same size. And by same size, we just mean has the same amount of vectors. All right, so to do this, let's suppose let V1 through Vn be a basis for V, okay? And let's let U1 through UM be a set of vectors in V. So we've got two cases to sort of do. We have to say, okay, if U1 through UM has more vectors than N, we have to show that it will not be a basis. And if U1 through UM has less vectors than V1 through Vn, we have to show that it's not a basis. Because if we do that, then we're going to be showing that every basis must have n vectors in this case. So to start with, we're going to have case 1. We're going to assume that m is greater than n. So we're going to assume that this set here has more vectors than this, and we need to show that U1 through UM will not be a basis. So in other words, we're saying that if you take a set of vectors that has more vectors than your basis, then it will not be a basis. Then after we've done this case, we'll go ahead and assume that m is less than n, and we will show that it cannot be a basis. And that will tell you guys that the only bases that are possible are ones that have exactly the same amount of vectors. So we're going to assume that this guy has more vectors, and we're going to show that it's not a basis. What we're actually going to do is we will show U1 through UM is linearly dependent. If we can do that, then that will mean that it is not a basis, because remember, to be a basis, you not only have to span, but you also have to be linearly independent. So if we can show that u1 through um will be linearly dependent, then it will not be a basis. So this will imply not a basis. Okay, so remember though, recall, v1 through vn is a basis for v. So v1 through vn spans v, right? To be a basis, that means you both have to be linearly independent and you have to span. So v1 through vn spans v. So what that means is we can write each of these u1 through um in terms of v1 through vn. So we can say that u1 is equal to, let's just say, a11 v1 plus a21 v2 plus dot 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 plus we'll say an1 vn. In other words, we can take the first thing in this set u and write it in terms of v, where these a11, a21, an1, those are just constants. We can do the next. u2 would be a12 v1 plus a22 v2 plus dot 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 an2 vn. Okay, and of course we could continue on and go all the way to u sub m, which would be a1m v1 plus a2m v2 plus dot 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 anm vn. So in other words, we're saying that those u1 through um can be written in terms of v1 through vn. Okay. All right. Now, remember, our goal is to show that u1 through um is linearly dependent. So, to show u1, u2 to um is LD, we need to consider the equation c1u1 plus c2u2 plus dot 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 plus cmum equals 0. Right? This is always the type of equation you consider when you're thinking about linear independence or dependence. Remember, if we can show that there are an infinite amount of solutions to this equation, then that is the same as showing it is linearly dependent. Remember, linear independence would mean that these constants have to be uniformly 0. Okay, we've got this equation. It's going to be really messy, but let's plug in what we know about u1, u2 through um into this equation. So this would then look something like c1 and then parentheses a11 v1 plus a21 v2 plus dot 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 plus an1 vn plus c2 times a12 v1 plus a22 v2 plus dot 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 plus an2 vn plus dot 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 plus cm. We'll see if we can fit it here. It doesn't look like it, so we'll just put it onto the next line. Plus dot 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 plus cm a1m v1 plus a2m v2 plus dot 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 anm vn equals 0. Okay, so all we're doing there is we're replacing u1, u2 through um with their representations in v. Now, let's go ahead and gather everything in terms of v1, so all these pieces, and then everything in terms of v2, these pieces, and then everything in terms of vn. So, if we think about that, that would give us something like c1 a11 plus c2 a12 plus dot 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 cm a1m all times v1. So all I did there is I gathered this, and I gathered this, and of course everything in between for all the v1s. Then we could talk about everything that's v2. So that would be c1 a21 plus c2 a22 plus dot 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 cm a2m all times v2. So there I distributed the c1 onto this, c2 onto this, cm onto this, put all that together. n plus dot 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 plus, and now we'll do the same for the n's here. So looks like we should get C1 AN1 plus C2 AN2 plus dot 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 CM ANM VN. Okay, and that was just gathering this guy onto here, this guy onto here, this guy onto here, putting all those together. And of course, that still equals 0. Okay, now, if we take a look at this, right, what we need to recognize is that this is an equation where these constants here are multiplied with V1, V2 through Vn, and has to be equal to 0. But remember, V1, Vn is a basis, which implies V1 through Vn is linearly independent, right? Since V1 through Vn is a basis, it must be linearly independent. That means these constants must be 0. Because if you're linearly independent, the only solution to this type of equation is that these constants must be 0. Okay, so let's grab that and move that onto the sort of next page here, because we'll need to use this here. So we'll just grab that. There we go. Okay, let's move that onto the next page here. All right, there we go. So like we just said, since V1 through Vn is linearly independent, each of these things here must be equal to 0. So we get that C1A11 plus C2A12 plus CMA1M equals 0. We get that C1A21 plus C2A22 plus CMA2M is 0. And we get C1AN1 plus C2AN2 plus CMANM. Oh, well, we should put our dot dot dots there. There we go. Dot dot dot. And then C1AN1 plus C2AN2 plus CMANM also equals 0. Okay. Now, this is pretty messy, but what I want to do is I want to rewrite this, right? Not by changing anything, but just by flipping these, right? So I'm going to write the A's first and then the C's to make this a little bit clearer. So this is the same as saying A11 C1 plus A12 C2 plus dot 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 A1M CM equals 0. A21 C1 plus A22 C2 plus dot 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 A2M CM equals 0. All the way down to AN1 C1 plus AN2 C2 plus dot 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 ANM CM equals 0. Okay. Now, a couple things to think about with this. What sort of system of equations is this? Well, everything in here, all the A's, all the C's, all of these are just constants, right? So this is just a normal set of equations. It's not a vector set of equations. It's a normal system of linear equations. This is also homogeneous because everything is equal to 0 there. Which are the constants that we're actually trying to solve for? Well, if you go back, I know it's a sort of lengthy proof, right? But what we needed to show, right, is our goal is trying to show that U1 through UM is linearly dependent. So we're really thinking about solving for C1 through CM. So back over here, right, treat C1 through CM as our variables. So what do we know about this system then? Well, there are M variables and there are N equations. So what this tells us is we have a homogeneous system with N equations and M variables. Okay, but we know a little bit more. Remember, back from our assumption, right, that M is greater than N. In other words, in this system of equations, we have more variables than equations. Since it's homogeneous, we know it automatically has solutions, and we know that this guarantees that it has infinite solutions. This has infinite solutions with m minus n, which must be greater than 0 because we assumed m is greater than n, free parameters. So this tells us u1 through um is linearly dependent. So we went ahead and we handled case 1 here. We showed that if you have more vectors than in the basis, you are automatically linearly dependent, so you cannot also be a basis. The whole trick here was to reduce our sort of proof into a homogeneous system of equations, and then realize since we have only n equations, the rank of this system must be n, so that the number of solutions, the number of free parameters for the solutions, is m minus n, which must be greater than 0 because we're working under the assumption m is greater than n. Okay, now we have to go ahead and talk about case 2. Case 2 will be a lot faster though. So case 2, right, we're going to assume m is less than n. So now we need to go ahead and show that if the set of vectors u1 through um is smaller than the original basis, well, then it must also not be a basis. So we handled what happens if it's larger. Now we need to talk about what happens if it's smaller. So let's go ahead and do that. And I apologize for some of the background noise, but we're just going to have to power through here. So let's go ahead and assume m is less than n and try to show this. To do this, we're going to do a proof by contradiction. Okay? So we're going to do a proof by contradiction here. For this proof by contradiction, what we're going to do is we're going to assume u1 through um is a basis. Okay, so u1 through um is a basis. But by the previous case, then v1 through vn, which has more vectors, will automatically be linearly dependent. That's what we just showed in the previous case. We said that if you have a basis and you have more things than that basis, it's automatically linearly dependent. But remember, v1 through vn is a basis, so it can't be linearly dependent. So this is a contradiction. This is a contradiction since v1 through vn is assumed to be linearly independent. And there we go. We've gone ahead and we've proven that every basis for a finite dimensional vector space must be of the same size. All right, so let's go ahead then and talk about some follow-ups from this and see that we can actually talk about the dimension of a vector space. All right, so since we can go ahead and talk about this now, we can actually define the concept of a dimension of a vector space. So the number of vectors in a basis for a vector space V is called the dimension of V. And we write this as dim of V. Now, the whole point of this, or the reason we say this definition now, is because we just proved in the previous part that every basis has the same size. So it's a well-defined concept to talk about that size. If we hadn't proven that previous theorem, we wouldn't be able to state this definition, because we'd say, okay, how do we know the size of the basis is the same? How do we know the dimension of V is actually a single value? Now we know every basis for a given vector space is the same size, so we know that dimension of V is a well-defined concept. So the dimension of V is just simply the number of vectors in any basis for that vector space. As two quick follow-ups to the proof that we just did, if the dimension of V is equal to n, then any set of more than n vectors in n is linearly dependent. How do we know this? Well, it's actually what we did to prove that first case. We showed that if you had more vectors than the basis, you're automatically linearly dependent. So follow-up 1 is just stating that that's how we proved the first case. Follow-up 2 says that if the dimension is n, so if the basis has n vectors, then any spanning set has at least n vectors. Now, for this one, I'm just going to give you guys a quick verbal explanation. I believe your book actually goes through a short proof of this. But basically, the idea here is if you could find a spanning set that has less than n vectors, well, remember, we said that any spanning set regardless of whether or not it's linearly independent or dependent, has a linearly independent subset that has the same span, because you can delete any linearly dependent things without changing the span. So if you had a spanning set that had less than n vectors, well, you could make it even smaller and keep it as a spanning set. But if you made it smaller, it would become linearly independent. It would become a linearly independent spanning set. That would become a basis, and it would violate the rule that every basis is the same size. So this tells you that if you know the dimension is n, then you know that every spanning set has at least n vectors. Okay, so now that we've talked about this concept of the dimension, let's go ahead and discuss a couple of the sort of dimensions in what are called standard bases for some of the common vector spaces we've been encountering. All right, dimensions of common vector spaces. So each of these I've sort of stated, we'll go through one by one here. The dimension of Rn, unsurprisingly, is n. I want to give you guys just a quick example of that, right? So let's say we consider R4, right? I want to give you guys what is often called the standard basis for R4. What's the standard basis for R4? Well, it would be the set of vectors 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Okay, am I going to prove it's the basis for you guys? Not really. I hope that you guys can clearly see it's going to be linearly independent, and I hope you guys can also see that anything, say, in R4, anything A, B, C, D can be built out of this by simply taking A times this, B times this, C times this, D times this, adding them up. So this is a linearly independent spanning set, and it would span all of R4. Hopefully this also justifies for you that even though I did an example of R4, if you had Rn, you'll always just use the sort of basic vectors here, and you can always use n of those vectors to build a basis. So the dimension of Rn is always just equal to n. All right, next one, the dimension of the polynomial space, Pn of R, is always n plus 1. To do that, let's go ahead and take a look at this example. I'm just going to do one example so you guys understand the logic here. P2 of R, right? So this would be the space of all polynomials of degree 2 or less. What's a standard basis for this? For P2 of R? Well, as you can imagine, you could use 1x and x squared, right? Certainly 1x and x squared, if you want, you can go ahead and verify that those are linearly independent. And certainly anything in P2 of R can be thought about as something like a times x squared, b times x, and c times 1. So it's certainly a spanning set. Now, when I give these standard bases here, are these the only bases? No, of course not, right? But they do tell us the size of the bases by the previous theorem. So you can see that for P2 of R, how many vectors do we need for its standard basis? We need 3, which is why the dimension in general is n plus 1. If we wanted to talk about P5 of R, we would need 6 different polynomials. All right, last sort of one I want to talk about here is the dimension of the m by n matrices. It turns out that that dimension is just m times n, which tells you that that concept of dimension is directly related to the concept of the size of a matrix. So, as an example here, let's consider, how about M2, 3 of R? So the 2 by 3 matrices. What would be a standard basis? Well, the standard basis, why don't we just use the same sort of idea here and basically keep everything 0 except for a single 1 in one element? So we could do things like 1, 0, 0, 0, 0, 0, and then 0, 1, 0, 0, 0, and something like 0, 0, 1, 0, 0, 0, and 0, 0, 0, 1, 0, 0, and 0, 0, 0, 0, 1, 0, and then 0, 0, 0, 0, 0, 1, and there we go. How many vectors do we have in here? Well, we've got 1, 2, 3, 4, 5, 6, which makes sense because 2 times 3 gives us 6. As a side note here, you guys should recognize that for square matrices, MNR, the dimension of that MNR must, by the same logic, be n squared, because you have a square matrix C. N times n will give you n squared. So for each of these, I'm showing you guys just the concept of the sort of standard basis, and then using that to justify this general statement about the dimension. Now, do keep in mind that these are stated to you guys now, so now you know the dimension of each of these three main vector spaces that we keep encountering. Do keep in mind that one of the sort of common vector spaces is not stated here. We're not making any mention right now about the vector space of continuous or differentiable functions. That turns out to be an example of a infinite dimensional vector space. It does not have a basis. So that one is not listed here because the concept of dimension doesn't really apply. And we'll actually prove, or at least discuss that in the next video. All right, so now you guys have seen some standard spaces and seen their sort of standard bases here. We want to talk a little bit more about some other follow-ups to the concept of basis. So let's go ahead and prove a couple more important theorems here. So we're going to suppose that the dimension of V is equal to n, and we're going to show that if you have any set of n vectors that are linearly independent, they will automatically form a basis. So to prove this, what we need to do is we need to show, well, we're going to assume that V1 through Vn are linearly independent, so that's half of being a basis. We need to show that they're going to span. So we need to show V1 through Vn will span V. If we can show that, then we know by assumption that they are linearly independent, and we will prove that they span. So being linearly independent and spanning, that'll automatically mean that they are a basis. So let's go ahead and let's let V, some random vector, be an element of V. To show that V1 through Vn span V, we need to show that there's some linear combination of V1 through Vn that equals V. Well, consider the set V1 down to Vn, comma V. This has n plus 1 vectors. Okay? Now, we're supposing that the dimension of V is n. So by what we just showed, right, if you go back to this, right, we said follow up 1, if the dimension of V is equal to n, then any set of more than n vectors is linearly dependent. Okay? Well, this is a set of more than n vectors, so this guy is linearly dependent. So V1, Vn, comma V are linearly dependent. So there is a solution to C1V1 plus C2V2 plus plus CNVN plus KV equals 0, where not all the constants are 0, right? That's what it means to be linearly dependent. There's some solution to this equation where not all the constants are 0. Now, I'm going to claim that not only do we know that not all the constants are 0, we specifically know that k is not 0. We know k doesn't equal 0 because if k was equal to 0, then there'd be some collection of C1 through Cn, where not all of them would be 0, that would be a solution to this. But that would make V1 through Vn linearly dependent, but we know that V1 through Vn are actually linearly independent. So we know that one of the non-zero constants must be the k. So we know that k is not equal to 0. And that's since V1 through Vn is linearly independent. Okay, so let's go ahead then and see what we can do with this. Let's go ahead and bring all these guys onto the other side. So we get KV is negative C1V1 minus C2V2 plus negative CNVN. And since we know that k is not 0, we can divide k on both sides. So we get V is negative C1 over k V1 minus C2 over k V2 plus minus Cn over k Vn. And that's exactly what we wanted, because each of these is a constant, and this shows us that V is a linear combination of V1, V2 through Vn. So V is in span of V1 through Vn. And remember, V was just some arbitrary vector in the vector space V. So this tells us V1 through Vn spans the entire vector space V. Okay, so V1 through Vn spans all of V. By assumption, V1 through Vn is already linearly independent. That means it automatically forms a basis. All right, so we did it. So we showed that if you know the dimension is n, then if you know you have a set of n vectors that are linearly independent, they automatically will form a basis. Okay, we're actually now going to show a very similar statement regarding the span and how that implies linear independence. Okay, so as our theorem here, we're going to suppose again that the dimension of V is equal to n, and then for any set of vectors V1 through Vn that spans V will form a basis. So what do we need to show here? We need to show V1 through Vn are linearly independent, right? We're by assumption, we're saying that they span V. To form a basis, they need to span V and be linearly independent. So we need to show that they're linearly independent. Okay, so how are we going to do that? Well, we're actually going to do that as a proof by contradiction. So, proof by contradiction. So let's assume V1 through Vn are linearly dependent. That means there is a linearly independent subset of V1 through Vn that is linearly independent with the same span. Okay. Remember, that's something we proved a couple videos ago. We said that if you have a set of linearly dependent vectors, you can always find a linearly independent subset. You can delete the linearly dependent ones, and you'll keep the same span. So there's some linearly independent subset of V1 through Vn with the same span. Well, that Li subset would span V, right? Because by assumption, V1 through Vn spans V. So since these guys have the same span, they would span V. And thus, be a basis. Okay? So that linearly independent subset would span V and be a basis. But remember, it's a subset, so it would have less vectors. This would mean we would have a basis with less than n vectors, which is a contradiction. Why is it a contradiction? Because we're supposing that the dimension of V is equal to n, and the very first thing we proved in this video was that the dimension is always the number of vectors in the basis, and that number is always the same for every basis. So it's impossible that we could have a basis with less than n vectors. So that's a contradiction. So if that's a contradiction, then our assumption that they were linearly dependent is incorrect. So V1 through Vn must be linearly independent. Thus, V1 through Vn is a basis. Okay. Now, at this point, we've proven a lot of different statements about the basis and the dimension and the concept of linear independence and span. So, I would recommend that you make sure you understand how we did these proofs, but for actually understanding what they all mean, we're going to do a quick summary of understanding how these statements relate to each other. So I don't often always do like a summary of every video, but I think this one, some of these proofs are pretty technical, so I think it's important to make sure you understand the proof, but it's also important to understand what all this means in the context of understanding vector spaces. So we're going to do a brief summary of this. So this is basically a summary of everything that you should take away from this video. So the very first statement, right, is that if a vector space has a basis, it is called a finite dimensional vector space, and we can write dimension of V since every basis will be the same size, right? That was the very first thing that we did, super, super important. Remember, not every vector space has a basis. There are infinite dimensional vector spaces out there. But if you have a basis, then every basis will be of the same size for that vector space. The second statement, and this is what we were just working on. We're saying that if you know that the dimension of V is equal to n, then if you have a set of n vectors, all of the statements are equivalent. If you know that they're linearly independent, then you know that they span, then you know that they're a basis. If you know that they span, then you automatically know that they're linearly independent, and you automatically know that they're a basis. And obviously, if you know that they're a basis, well, then they must be linearly independent and span. But the whole point of this, the reason that this is so crucial, is that if you know the dimension, then you really only need to check one of the two conditions for being a basis. In general, if you just have some random vector space and somebody asks you, is this a basis? You have to say, okay, I need to first prove that it's linearly independent, and then I need to prove that it spans, or vice versa. You got to prove both. But this statement here is saying if you already know the dimension, then showing one of the two is good enough because one implies the other in the case that you already know the dimension. All right, the third and final statement here basically says what happens when you differ from the dimension. So if you know that the dimension is equal to n, then anytime you have more than n vectors, you automatically are linearly dependent. That should sort of make sense. This is sort of saying this is the size of the vector space. If you take more things than the size, then some of them must depend on the others. There's just not enough flexibility for all of them to be independent. So anytime you have more than the dimension, you automatically are dependent. And if you ever have less than the dimension, then that simply won't span everything. In other words, that dimension is the exact perfect size where everything is independent, but it yet generates the entire space. If you have more than that, you're automatically including some dependencies, some repeats basically. And if you ever have less than that, well, it just won't build or generate everything in your vector space. So definitely look over these three statements and make sure you understand how these summarize everything we did in this video. In the next video, we'll actually investigate determining whether or not different sets of vectors are bases for vector spaces, and we'll really make use of this thing here and this thing here because computationally these are very useful facts. And then we'll finish up this section by giving an example of something that doesn't have a basis that is an infinite dimensional vector space.